All right, our next presenter is Yunus Zeytuncu, and Yunus is from the Department of Mathematics and Statistics. Yunus is he's a repeat performer, so we'll see if he's improved his form from last year. He's going to be talking to you about solving differential equations in different geometrics. Yunus.
Can you hear me well? All right, I think my microphone is working. All right, I will talk about differential equations and geometry, and I will focus on a particular sub-question, whether we can hear the shape of an object, or can we hear the shape of a drum. When we think about geometry, we think about shape, we think about area, we think about length, we think about volume, those sorts of quantities, right? And usually when we think about shape and other things, geometric objects, we usually attach visual images, right? If you give me a rectangle and a triangle and I can look at them and I can tell the difference. But I want to do that through hearing. So this might sound a little bit different, but we have a 6-month-old at home, and if I give him a rectangle and a triangle, he tastes them. That's how he tries to tell the difference. So I'm going to try to tell the difference by listening to it. All right, is that possible? Absolutely, and the key term here is vibration. And I want to start with a simple example, a vibrating string. And if you are a musician or if you're familiar with string instruments, you know this really well. Let's say you have a piece of string, the sound it will produce will depend on the length of it. That's actually how you produce different tones on a string instrument, by controlling the size of the string, right? So if you have a long string, it will sound in a certain way. And if you cut that same string, same material into a small piece and vibrate that, it will produce a different sound. So the geometry affects the sound. And the other way around is also possible. Let's say I had 2 separate pieces of string behind those curtains, and I vibrated them many times. And if you have a good ear, you could tell me which one is longer, which one is shorter. And if you even have a better ear, you can tell me the exact length of the string I'm vibrating behind the curtains. So this is something very common. All right, one-dimensional story, it's a good start. How about in 2 dimensions? Now, instead of a string, I will think about my instrument as a drum. So let's say you have a drum like that, and again, you go ahead and play it, you vibrate it. But now, unlike the string, vibrations can take multiple different forms. And again, you can hear different sounds depending on the geometry of the drum. But the inverse question, can you understand the geometry by just listening to it, is a challenge. And in this case, if I had 2 separate drums behind the curtains, and if I would start playing them, vibrating them in many different ways, you couldn't tell the exact shape. In 2-dimensional problem, by hearing the drum, you can tell the area, perimeter, and other things, but you cannot really identify exactly what that object is. And as you can imagine, in 2 dimensions, you can have different objects of the same area. You can have completely different shapes of the same perimeter. All right, so what is it for a mathematician then? This is a talk about mathematics, not music, right? All right, so when I talk about hearing the drum or the string, vibrations of a string or vibrations of any object, for a mathematician, that refers to eigenvalues of a certain differential operator. If you haven't had differential equations before, don't worry. This is a particular kind of differential operator called Laplacian, and it is very common in lots of fields. Very common in engineering, very common in any kind of distribution phenomenon happens, very common in finance industry. And for a mathematician, I want to solve a particular differential equation where this operator equals, acting on a function, makes a multiple of the other. So this number here that I use Greek letter lambda to denote that is what I mean by hearing. So for a mathematician, calculating these numbers on a particular shape is hearing. All right, so when I say hearing geometry, I mean from a mathematician's point of view, calculating the eigenvalues of that particular differential operator. This is exactly hearing the overtones of that geometric object. You have a geometric object, you vibrate it. It produces certain sounds, you hear them, and you try to understand the shape of it. For me, it is calculating those eigenvalues. The set of all eigenvalues, the set of all the frequencies, vibrations that come out of that particular shape, we call it the spectrum. So let's say you know the whole spectrum and you are trying to understand the geometry based on that spectrum. And this is not something new. This is quite old, and astronomical spectroscopy is just this idea. Has anyone seen a spectroscopy? So this was used long time ago to understand the planets and outer space. So what this does, this is not visually seeing a faraway planet, right? It collects the signals from outer space, in other words, vibrations. So it is to the set of eigenvalues of a certain differential equation. So those vibrations, those eigenvalues are received and they are used to understand the geometry of planets and outer space. All right? Has anyone used a spectroscopy? All right, so I'll bring this down to earth. You all use spectroscopy. You all use hearing to understand geometry. Anyone has a stud finder at their home? I don't have one. And if you don't have one stud finder, what do? Use the knocking method, right? So this is exactly the primitive spectroscopy. Why is that so? Because think about a piece of drywall and having a stud behind it versus no stud behind it, it's different geometry. So when you are trying to understand where the studs are, you are solving a geometric problem. You are trying to see how the geometry varies on the drywall. And how do you do that? You go and knock, you vibrate the wall, and you hear. So what you're hearing is actually the eigenvalues of a particular differential operator. And depending on those eigenvalues you hear, those frequencies you hear, you tell, okay, there's a stud here and no stud there. All right? So we all do that. All right, so these are all known stories. So what is my contribution? What is my part in this? I am not working on a string. I am not working on a two-dimensional drum head. I am not trying to just understand the studs behind a wall. I'm trying to do all these things in higher dimensions. So this is the favorite part of a mathematician. I can think about 7-dimensional objects, and they are not easy to visualize. We use differential equations to visualize them, these higher dimensional objects. So in my research, what I do, I usually study these differential operators on higher dimensional manifolds. And as you can imagine, the techniques we know how to solve these differential equations on a string or a drum head are not sufficient to solve this problem on higher dimensional objects. So what I do, I try to develop new techniques to solve these differential equations to calculate eigenvalues. But not just calculating the eigenvalues is my goal. My goal with my students is to relate those analytic data we extract from solving differential equations and relate them to geometry. So this way we can say this 7-dimensional object looks like that, but this other one does not look like that. All right? So that's what we do. Thank you.